Yep. Thanks, Luis. Good afternoon or good evening, depending on where you are, everybody. Yeah, today I want to talk about unscrambling quantum fields with local probes and machine learning. This talk is based on working in preparation, done in collaboration with Daniel Grimmer, Irene Melgarejo-Lermas, and Eduardo Martin Martinez. Well, instead of giving you an outline of the talk or anything, I'm going to acknowledge that the title might be a little bit weird. So I'm going to use my my first slides to flesh it out, and so that you can hopefully see what we are trying to do here. So let's start with a problem. You'll see that it's not the problem that I'm going to deal with, but it's going to be our starting problem. So you all know that quantum field theory is one of the pillars of modern physics, and that it gives us one of the best descriptions of nature that we currently have available. But any physical theory, if it's going to be useful, we need to know how in that theory we can describe how we gather information from the systems, the physical system that theory is describing. That is to say that we need to describe measurements. And in quantum mechanics, you'll know that the measurement problem is still open. But in practice, we can describe measurements using projective measurements and Luder's rule, which is the update rule that tells us what's the state of the system after we perform the measurement. However, we cannot use the same strategy for quantum field theory. We cannot extend projective measurements to QFT, as Sorkin pointed out in 1993. This was something that was treated in depth in yesterday's morning session. So if anyone is very interested in the problem and didn't attend that one, I will recommend that you check some of those talks. So this lack of measurement theory in QFT has been addressed in several ways. But one possibility is to use particle detectors. Particle detectors are localized non-relativistic quantum probes that we couple to quantum fields. The idea is really simple. We couple the detector to the field so that through the interaction, the detector gathers information from the field. And then we measure the detector. And that measurement, we know how to describe it because the detector is non-relativistic quantum system. So this detector-based measurement theory arguably gives us a measurement theory that has all the properties that we should ask a measurement theory to have. And because it gives us a proper measurement theory, that's why in this work we are going to use particle detectors, local probes, to deal with measurements, to deal with measuring quantum fields. In any case, however we decide to model local probes, whether they are non-relativistic quantum systems or they are quantum fields or whatever, what we always have to acknowledge is that measuring quantum fields in general always takes place through interaction with localized probes, whether that be a detector in LHC or a human retina or a photodetector. So our measurements are always going to be localized. So that maybe that's the question: what if what is the thing that we want to measure is a global feature of the QFT? Well, luckily for us in that case, when a quantum field is in equilibrium with its environment and its background, it stores locally information about its global structure. The problem is that it does so in a scrambled way. What does this mean? It means that there is not a local observable that we can measure so that we measure the global feature. But the outcomes of the local measurements are going to be conditioned by the global features. In this sense, we know that by looking at local measurements, we can tell things about the topology of our spacetime and the boundary conditions, whether the spacetime is expanding or not, and several other things. So our goal here is to find an efficient way of extracting this local information to tell things about global features. This is what we mean by unscrambling quantum fields. Now, if we want to deal with this problem seriously, we have to understand what's going on here. So given an arbitrary feature of interest F, any experimental design is going to include at least two fundamental elements: a measurement protocol, MF, that is going to give us an array of data D, and a data analysis function F that is going to take that string of data D, and it's going to output whatever thing we are interested in about F. Right? Now the problem is, what if we consider a different feature F prime? Well, it is almost always assumed, and it's usually not questioned, that if we want to measure a different feature, then we have to use a different measurement protocol and a different data analysis function. Because our measurement protocol should be tailored so that we are targeting the specific feature that we're interested in. Well, here I want to challenge that notion. Could we use the same protocol, and let's call it M0, for a wide variety of different features? Well, it turns out that precisely because we are measuring with detectors and they are very simple and they have only a little, only a few degrees of freedom, there is a simple measurement protocol and not with which we can essentially extract all the information that is available for a detector when it's measuring. Of course, in that case, the problem is that we target an arbitrary feature of the quantum field, then our data analysis function is going to be very complicated. And there is when machine learning can help us, because neural networks are specifically designed to deal with complicated high-dimensional functions. Now, machine learning techniques have already been used successfully within quantum mechanics and in lattice QFTs. But our goal here is to show that combining machine learning techniques with detector tools in QFT, one can avoid the complexity of designing specific local measurement protocols and translating them into concrete claims about the quantum field theory. And instead, we can just use a very simple fixed measurement protocol, offloading all the complexity into the data processing, which is then handled easily via machine learning. So now that we have our goal set, let's describe the general framework that we're going to deal with. First of all, I have to clarify that this general framework does not depend on the particular particle detector model that we used. However, here for simplicity, we have considered that we have a foliation TX in an n+1 dimensional spacetime, and that there we have a particle detector D coupled to a quantum field phi in a local way via the interaction condition that we have there. That is just a linear coupling. This is an unruled away detector. We know it's very common in our field to use. Also, for the sake of simplicity, we are going to use a reference example when we describe the general framework, in which the feature of interest is topology. The question that we want to answer is whether the topology is open or closed. And the detector is going to be a harmonic oscillator with that free Hamiltonian, where QD and PD are the unitless quadrature operators. So the general framework has three main ingredients. The first one is a simple fixed measurement protocol and not that we mentioned before. What is going to be this measurement protocol? Well, first of all, we have to initialize the field according to some conditions labeled Y. What is this label Y? Well, this label can be the temperature, it can be the boundary conditions, or in particular, in the reference example that we are using, it's going to be open or closed. That is telling us what's the topology. Now, the second step is to initialize the probe to its ground state and then couple it to the field starting at time t = 0. Then at time tm, we perform a projective measurement on the quadrature QD of the detector and we record the result. We then repeat steps 1 to 3 by measuring the quadrature PD, and then RD, which is a combination of QD and PD that allows us to extract information for the correlations between PD and QD. Then we repeat the same thing, but measuring at different times and increasing the time uniformly. And then we repeat the whole process n times. So you see how this measurement is simple and it's clearly untargeted. We are not thinking about any particular feature. It yields a string of raw data that is associated specifically to the label Y with which we initialize the field. Of course, since we want to train on neural network, we are going to feed it with a lot of different examples. So we want to collect n samples of these pairs of raw data with the label Y. Now, the second ingredient is data preprocessing. This only serves the purpose of making life easier for the machine learning algorithm, so that it's also more efficient. Basically, here we realize that each one of the n-tom measurements that we perform at the same times are independent. So we can just summarize them using sample means and sample higher the central moments. In particular, in the two examples that I'm going to talk about afterwards, we only consider up to 4 central moments, so that our compressed data only comprise the sample means, the sample variances, and the sample 4 central moments of each one of the 3 variables that we measure for each one of the times at which we measure. Now, the third ingredient is the neural network training. As we said, the neural network is going to provide us with a data analysis function that is going to translate our data into a specific claim about the feature of interest, right? We have said that the neural network is suitable for this task precisely because it is designed to model complicated high-dimensional functions. But how does it do this? Well, it does so by alternatively applying tunable linear transformations that depends on certain weights and bias, and fixed nonlinear functions that are called activation functions. So here in this figure, you see a representation of a neural network that could be used for the example, the reference example that we are talking about with the open or closed topology. And you see that it's formed by edges and nodes. The edges, well, once we input the data collected by the local probes, the edges represent the applications of linear transformations, and the nodes represent the applications of the fixed nonlinear functions. Now, we have said that the linear transformations are tunable, while the nonlinear functions are fixed. But how do we tune them? Well, this is where the training procedure comes in. What we are going to do is to feed the neural network with some training data, and we are going to ask it to adapt, to tune the weights and bias of the linear transformations so that a particular cost function is minimized. In the case of a classification problem, as the one that we are dealing with in the example, that cost function is basically going to be a relative entropy. In the case of a regression problem, like for example, estimating the temperature, as we're going to see in one of the examples, it's going to be mean square error. Also, for those familiar with machine learning, maybe, we always introduce the L2 regularizer to avoid overfitting. But if you're not familiar with it, it's not very important. So, well, now that we have introduced the general framework, I'm going to show you a couple of examples in which we have used this general framework, hopefully to convince you of its power. Of course, since we are theoreticians, we didn't actually perform the experiments, but instead we just simulated the data. So our first example is remote boundary sensing. The setup is that we have a cavity of length L, and we have one probe coupled to one of the ends. And the problem is that we want to determine the location of the boundary at the other end of the cavity. How did we simulate the data? Well, I don't want to get into the details, but basically the idea is that since the probe is localized, the field is effectively unlimited, so that after applying an extra approximation, we check that was safe, we can basically reduce the problem to deal with a lattice. And then, since the initial states are Gaussian and the interaction is also Gaussian, we can keep track of the evolution using Gaussian quantum mechanics. Now, for this problem, we consider three different labels. Since we are working already in the lattice, we consider that the probe is coupled to the first side. And then the problem is going to be to distinguish whether the boundary is at the last side or the second to last side. In the case of label 1, what we have is that the last side is coupled to the second to last side, and therefore the boundary is in the last side. Meanwhile, in the second case, we have that the last side is going to be not coupled to the second to last side, and therefore the boundary is in the second to last side. And we added a third one. Why did we do this? Well, we have to keep in mind that our goal is not only to see if we can figure out where the boundary is, but also we want to see if we are guessing that by extracting local information, not by receiving a signal from the boundary. So this case is precisely that. It's a case in which the detector is receiving a signal from the boundary. That way, what we have done is to ask the algorithm, the neural network, to distinguish between cases 1 and 2 and cases 2 and 3. So that any performance over 50% that we get for distinguishing between cases 1 and 2 is going to be due to extracting local information. Unlike, because that's anything that happens before the light crossing time between the boundary and the detector. That is after that, the algorithm is going to be able to tell the second and third cases apart, and therefore that's when we can tell that it has received the signal, and we cannot argue anymore that the success of the prediction is due to extracting local information. And indeed, this is what happens. We can see that that the algorithm performs reasonably well way before the red line, that is the light crossing time between the boundary and the detector, which is precisely the point at which the algorithm is capable of distinguishing between the second and third cases. Now, what we have done here is that we have seen where the boundary is without actually sending a signal to it and getting it back. This phenomenon of seeing without light is not really new. It has been seen and well understood in many different contexts. What is new here is that we have explicitly collected simulated data, and we have directly translated them into a claim about where the boundary is. And moreover, we have done this with a one-size-fits-all method that was not tailored at all for this problem in particular. Now, our second example is about thermometry. The setup is exactly the same. We just use different parameters for the length of the cavity and the size of the detector, but basically it's the same. The problem is to estimate the field's temperature within a 1% accuracy. And then for simulating the data, we use the same physics. We also use the latest approximation. We use Gaussian quantum mechanics and these the boundary conditions. And for each base temperature, T, that is the T's that you see here, we fitted the neural network with temperatures between 0.9 T and 1.1 T. Since we were asking it to give the field's temperature within a 1% accuracy and the range is limited, the baseline performance of the algorithm would be 10%, which is just random guessing. We see here that the algorithm performs way better than that, way before the red line, which is the Heisenberg time, which is the lower bound for when the detector thermalizes. So we see here that we are figuring out the field's temperature, again, by extracting local information, because we are not measuring the temperature of the detector and then argue that the temperature of the detector is the temperature of the field, because we are measuring the field's temperature way before the detector thermalizes. So all in all, we have described one-size-fits-all method to extract information about QFTs through local measurements. And specifically, we wanted to read out non-local features of a QFT from the outcomes of a fixed measurement protocol that used only local experiments. We showcased how machine learning techniques allow us to shift the burden, the complexity from experimental design to data processing. And finally, we demonstrated the power of this framework by applying it to two examples that are of different nature. So that's all. Thank you all for listening. And if you have any questions,
thank you very much, Jose. So, as Jose was saying, any question? No questions?
Hi, Jose. Can you comment on whether you could try to simulate more convoluted setups, such as, for instance, the Unruh effect or even Hawking radiation or something like that?
Yeah, actually, we expect it to be. It's one of the things that we are working on. We expect it to be applicable to that kind of setup too. Yes, in principle, we expect it to be applicable to really wide variety of features and setups. Because as you see, the whole point of it is that the detector is a very simple system. So there is a simple measurement scheme with which you can basically extract all the information. It's true that you're going to have a lot of information, a lot of data, but precisely because machine learning is good at handling that amount of data and at producing very complicated functions, in principle, you can expect to work basically in any kind of setup that you can think of.
I see. What would you think would be the implications of being able to simulate Unruh effect, for instance?
Well, I mean, at first, at the very least, I would expect it to definitely enhance the sensibility. We haven't exactly seen how much that could be, but at the very least, that's what I would expect. Yes, I mean, that's basically all I can say. I would expect to increase sensibility. I don't know if it would be enough to get to a threshold that made it measurable. But, yeah.